Thanks, Alice, and thanks for the Solon Foundation for funding to attend this conference. It's great to see a mix of mathematicians and cryptographers. Um, Myself, I'm a cryptographer, from the ground. I've been looking into this more mathematical, uh, this type of group theory recently, and from the mathematician, apologies in advance if what I'm saying is going to sound strange, and from that, I learned this thing myself. And this collaboration is based on a couple of joint work with people, mostly at City University of New York and let me just start with an overview so we see what we're going to be talking about today. So the goal of this project is, it's not just this paper, but like it's a research project. We're trying to come up with the source of interactivity assumptions that are different from what you're used to. Of course, we'd like them to be viable for cryptography, and we like them to come from combinatorial group theory. So by viable for cryptography mean that, of course, they should have cryptographic applications, but we should also get some sort of evidence that this problem are conjecturally hard. And unlike other approaches, we are taking the reverse order. I'm trying to go for the evidence of hardness of interactability before we can come up with lots of applications. So, for example, unlike the previous talk where the upshot is hopefully we can get noise-free FHE if we can get reasonable groups, here I'm saying let's see what kind of assumption we can get some good confidence that are going to be interactable over non-commutative groups, and then let's see what kind of cryptography we can make out of it. So I'm going to be talking only a little bit toward the end about cryptographic applications of the assumption I'm going to be discussing. Instead, most of the time is going to be spent talking about the cryptographic assumption we're looking at, the specific group theoretic setting where we are instantiating it. Again, to differentiate this from other work on non-commutative cryptography or cryptography based on non-commutative group, our approach doesn't really start from group theory and then, look at problems that are well studied in group theory and try to figure out how hard they are on average for cryptographic purposes. Instead, we start from the cryptographic approach. We look at problems, in particular our approach. We look at one set of problems that has been very successful in cryptography, the learning with errors problem and the learning parity with noise, which is a related version of the problem. And we try to see whether we can generalize that to make it work on non-commutative groups. I'm going to talk about that in a bit. We'll see that those make sense for vector space over finite fields, and we generalize them to work on any groups, and then we try to find instantiation of that approach over groups which are not necessarily abelian. And so that's kind of going to be our approach. And as in outline, I'm going to start with kind of a primer on what these Burnside groups are, just to set some terminology, because they're not familiar to most cryptographers. And maybe even for the mathematician, my terminology may be slightly different. For example, I noticed that in Nuda's talk before, commutators appear with the right convention, whether I'm using the left convention, or perhaps the other way around. Like there are two conventions which are just a matter of how you write the inverses, and they use the opposite. So unfortunately, it's going to be hopefully not too much confusion, but with slight clash notation with the previous talk, for example. So I want to establish notation first. And then after we talk about these Burnside groups, we refresh what they are for people that know them, or we have a look at them for people that haven't seen them yet. I'm going to discuss a specific interactivity assumption that we're going to be looking at. After that, I discuss some evidence why we believe this assumption may be a good assumption for cryptography, why there may be some average case hardness in that problem. And then I'll briefly discuss what kind of cryptographic application we get. And just to give away the bottom line for cryptographers, so far we only get mini-groups. So forget about FHE. Right now, we don't even get public key encryption. So in terms of applications, we have a way to go. And another way to see this talk is as a plea for help from mathematicians to help us figure out this part, and cryptographers to help us figure out this part. So if you're looking for problems, I'm not going to spell them out explicitly, but there's lots of problems. So talk me after the talk, or or during the talk. Feel free to ask questions and keep it interactive. Okay, so Burnside groups. You may have seen in the beginning the list of collaborators. Some of them are mathematicians, and in particular, one of them, Gilbert Baumschlag, who unfortunately passed away last year. He was our kind of oracle to come up with groups that would be usable. And we were telling him properties we wanted. In particular, we wanted to have groups for which we can have lots of homomorphisms between them. And at some point, he told us, what about Burnside groups? Have you guys thought about them? And we had no idea what he was talking about, what this was, what these groups were, unfortunately. So we went and looked into them, and just as a summary from somebody who didn't look at this, during his graduate studies, these Burnside questions, came about asking questions about the local to global principle. If you know something locally about the group, what can you infer globally about the group? Similar to the Chinese-Riemann theorem, but in another point of view. In particular, what they're saying is, suppose that you know that the group is locally finite. No matter which element you take, each individual element has a finite order. Can you tell for sure that this group is going to be finite as an whole? You have a finite number of generators, and any element in its own is finite, is periodic, has a finite order. The question is the group going to be finite or infinite? And then, of course, you can try to make specialization. This is called the Burnside problem. And turns out that you can have infinite groups even though the order of the element is finite. And then people have looked at more precise questions like, okay, suppose now I tell you that the order is not just finite, but it's bounded by some given number for all the elements. Now can you tell me more about the group and what's the structure? And people look at that called the bounded Burnside problem because now you have a bound. And people also look at the restricted Burnside problem, which doesn't arise for our purpose. So really what we're interested in is more like the combinatorial structure that comes up in the bounded Burnside problem. And in particular, when you're looking at the bounded Burnside problem, so you have a bound, or what's the largest order for every element in the group, and you call this bound M in here, then the important object to study are going to be these so-called free Burnside groups. So let me try to describe what these are because they're going to be central to what we're going to discuss. We're going to be denoting them with D and M, where N is the number of generators. You can think of the generators as indeterminates, like in a polynomial, multivalent polynomials, just formal indeterminates. I'm going to use x1 to xn. And then you ask the condition that every element that you make up out of these generators is going to have an order which divides M. And in practice, we're going to look at prime M's. So in order to divide M, it's going to be exactly M. So it's different from the way that we usually think about groups, in that we don't start from a group operation and try to understand the structure of the groups that come about. It's the other way around. We start from the properties that we want, and we try to see what's the group operation that achieves this property if you impose no other restrictions on the group. You say, I care about the group which is the most generic group possible, so long as it has this property that every element divides M. So in terms of notation, this means you have a bunch of generators, like indeterminate in a polynomial x1, xn. Elements in this group are just going to be sequences of generators and their inverses, bounded length, finite sequences, but of any length. And a priori, they could be all different. And then the question is whether they're going to be equalities that are going to be holding in these groups. And of course, the identity in this group is going to be the empty sequence. I'm going to use the multiplicative notation. So it's going to denote the identity with 1. It's going to be in the empty sequence. And you have the trivial conditions, which are that xi inverse is going to be equal to 1. Xi inverse xi is going to be equal to 1. Other than that, the only other condition you want from the group is that the repetition of m copy of any word is going to be the identity. And that's that. You want no other conditions on the group. So the free Burnside groups with n generator and exponent m are the most generic possible group you can get if the only condition you impose is that the identity is equal to the trivial factors xi, x inverse, xi, and repetition of m times the same sequence of symbols give you the identity, and that's that. Now let's look at some examples. So if you look at 4 generators and exponent 3, we're going to be looking at exponent 3 in the rest of the talk, so I'm going to start using exponent 3. Then here is an element, x1, x4 inverse x1. It's a repetition of element. In this case, I chose to pick 3 of them. First one is x1, second is x4 inverse, and then I have x1. Also, x1 inverse, x4 inverse is an element in this group because it's a different sequence. And now you may wonder whether these elements are actually the same element or not. And why would they be the same element? Well, because I'm talking about condition exponent 3. So this Wm equal to 1 means W cube equal to 1. Well, if the cube of everything is 1, then the square equals the inverse. So if the exponent is 3, the squares are going to be equal to inverses because this means x1 cube is 1. x1 squared is x1 inverse. And now, if you multiply x4 inverse in the middle here, you would hope that x1, x4 inverse x1 is the same as x1 inverse x4 inverse, and it's not. This group is non-abelian. So even though, of course, x1 inverse x4 inverse is equal to x1, x1, x4, because x1 inverse is equal to x1 squared, you have that x1, x4 inverse x1 is not x1, x1, x4. You can't commute them. Okay, so this group is non-commutative, but it has some nice properties. You don't need to care about squares. It's going to be the same as inverses. So in the following, you're going to see my exponent just going to be 0, 1, and minus 1. All the elements present or not present or inverses, because squares are the same when they're being the exponent. What is that? Sorry, yeah, thank you. I have a typo here. This was supposed to be x2 inverse. Thank you. Yeah, this was just x1 supposed to be square. Sorry about that. All right, so some equality that you expect don't hold. On the other hand, there are some strange equality that holds, and they're gonna have consequences later on. For example, x1 x4 inverse x1 equals x4 x1 inverse x4. It's kind of strange, like is which the order is which one is inverse. Why is that? Well, just multiply everything on the right. You get x1 x4 inverse, x1 x4 inverse, x1 x4 inverse. You multiply everything here on the right, and that's x1 x4 inverse repeated 3 times. And because we have this exponent condition, we're talking about 3 exponent here, then x1 x4 inverse 3 times is the identity. So because of this equality, you get this kind of equality. So you're gonna see these kind of strange things happening. It's non-commutative, but you have nice equalities just following from the exponent conditions already. All right, so these groups, like Burnside was a group theorist who started looking at this problem in the early 1900s, and it's been more than 100 years. And people have looked at them extensively, although the focus has mostly been on answering the question I started from the beginning. When is a group finite? When is it infinite? And in fact, there's a lot that we don't know still about that. For example, we know that if you enforce order 2, if you require that x squared is equal to 1, which means self-inverses, then it follows that you must have abelianity. Xy squared equal to 1, because if you use a case of exponent 2, then xy squared is equal to 1, y squared equal to 1 for every x and y. And of course, also xy squared is equal to 1. But xy squared means xy is equal to y inverse x inverse, and is equal to y is equal to x, so you get abelianity. So if you want condition of exponent 2, you get abelianity, which means you get nothing new. It's vector spaces, it's isomorphic vector spaces, f to n or addition, just so addition, not vector space, just the group under addition. However, as soon as you move to exponent 3, you get something different. It's no longer abelian. We saw before the case of 4 generators. And it's actually much larger than the abelianization case. And interestingly, it's finite. So there is a lot known about that. And we're going to be looking the rest of the talk on BN3. Now, if you look beyond BN3, look at BN4, turns out you can say it's finite because it kind of helps that you know about BN2 to figure out things about BN4. But as soon as you go into BN5 and you ask, is a group where you have 2 generators, and I believe it's already unknown for 2 generators, and the quintic question is all for every element. Is it finite or infinite? And people don't know. So before people know, you have to wait until you get a largish exponent. I believe already for like 150 exponents, 2 generators, it's infinite. But we don't know what happened with 5, we know what happened with 7, we know what happened with 6 again, because you can kind of break it down into, because 6 factors are 2 and 3, and some of these, some of these helps. And there are lots of deep results, like you have to look into Lie algebra, which I have no idea what it deals about, and people got the field medal because it showed that this is true not only for infinite odd, but also for infinite, not only for large m when it's odd, but also for large m when it's even. And there was an open like from 50 years to see that it's true for odd and even. So it's been studied a lot, but people don't look at the computational property of these objects, and so that's instead what we're doing. So because we don't know a lot about this, but we do know some about BN3, that's the group we're going to be focusing on. You can think of that as the first step removed from abelian case. If you use exponent condition 2, you have abelian groups. And so the first instantiation when you get non-abelianity is 3, so that's what we're looking at. There's no reason why you shouldn't be looking also at other case, maybe BN6, that's just what we'll be looking at. And because in the rest, I'm just going to be talking about exponent 3, I'm going to be dropping it from the notation. I'm just going to talk about Bn, where n is the number of generators that we have in our group. Yep.
The infinity of that will depend on n?
No.
B2n is
For B2,
finite and they're all finite?
I'm sorry, to repeat the question, yeah, no, I think may not depend. So I don't know too much of the results. I know that here, already for the case of 2, for some exponents, both odd and even, it's infinite, and the numbers here are in the hundreds. I don't know if it's an infinite, if like must be infinite for 2 and not to be infinite for 11. I'm not sure. Yeah. So I'm not sure. Of course, they get the cyclic because they're cyclic at the box. Yeah. I'm not sure if whenever it's infinite, it's already infinite for 2. That's my question. I don't know. Okay, so let me rewrite the notation what we saw before, now specializing for the condition of m equal 3, because that's all I'm going to be caring about. So this Bn, we call the free Burnside group. I'm going to drop the free in most of my terminology. Just going to say Burnside group. of exponent 3. And again, these are groups which are obtained with formal generators x1, xn. Think of them again as indeterminate in a multivaluable polynomial. Elements are sequence of the x and the inverses, and they condition that w is 1, no matter which w you take. And by most genetic, like I mentioned before, I mean that the only equality that holds are the ones that follow from this. You have no other conditions other than what's in here. Now, one consequence for a computer scientist is going to be that in order to describe the group operation in this group, we're not going to be able to explain it in terms of, okay, you do this, you multiply, you sum, and that's what you get. We have to reverse engineer it from the description of the group. We want this property, we're going to impose the minimum amount of restriction, so we're going to have to reverse engineer what the group operation is going to look like. And I'll talk about that in a moment. Unfortunately, it's not, doesn't have a very, I wish it had an easier way to describe it. As I mentioned before, it's non-commutative. Here is a way to see why. Well, commutative means that xi xj is equal to xj xi. Instead, it's going to be different. Because if you break it down, in order for xi xj to equal xj xi, you need this quantity to be 1. And this does not follow from that equation. This equation has at least length 3. And you can't reduce this here. The only place of length 3 don't reduce, and there is no other equation that you have. So this is not going to be true. So all these equations are going to be different. Generators are not going to commute with any of the others. They may commute with other elements, but not with other generators. And like I mentioned, the group operation is going to be defined by saying, okay, you want to operate on 2 elements, you just stick them one after the other. These are sequences, so you can always concatenate the 2 sequences. And then at the interface of the end of the first sequence and the beginning of the next sequence, maybe there's going to be some simplification occurring because maybe before there was no repetition. Now after sticking them together, there is some repetition. And then you have to spot them, simplify them, and you're going to get the result. So it looks like it's going to be messy, inefficient, and likely. Instead, there is a way to make that operation efficient. To discuss the group operation, I have to introduce this notation called basic commutators. And here is where I have the clash with the Nuida's notation. Commutators are going to be these elements denoted with the square bracket. If xi and xj are 2 generators, we call this a basic commutator. But the equation makes sense no matter what elements you have here. The equation is true no matter what the elements are. When the 2 elements are generators, we call this a basic commutator with 2. 2 because there are 2 elements. So it's defined to be xi inverse xj inverse xi xj. And you can think of that as, okay, so we don't have equality, we don't have abelianity. It's not true that xi xj equals xj xi. However, you can always force something like that to be true by adding the necessary quantity. So xi xj commutator, it's defined to be whatever makes this equation work. So xi xj commutator is the quantity such that xi xj equals xj xi followed by the commutator xi xj. So when we're going to be working with an example, you can think of that somehow, okay, you have xi xj, but you wish you had xj xi, then go ahead, you can replace them, but there's going to be a ghost left over of xi xj in the form of a commutator. And the interesting thing is that you can repeat this concept with the commutator of weight 3, which are going to be defining by, assuming that if you have 3 things, and again, if these are generators, we call this a basic commutator of weight 3, define the generator of weight 3, commutator of weight 3 xi xj xk to be the commutator xi xj, and then, like I said, this equation makes sense for every word. So it also makes sense for this word with this other one. And whatever, maybe I'm going to spell it out in the board, what that means, although it's just going to be, so commutator of xi xj xk is just going to be the inverse of the commutator of xi xj followed by the inverse of xk, and then the commutator of xi xj followed by xk. Okay, so you can build these things, in this order. And interestingly, of course, this is something you can do if you know group theory. This is something you can do in any group. And interestingly, in the case of Burnside groups of exponent 3, you don't need to look beyond the commutator of weight 3. And that's it's a non-trivial fact. It's not it's immediately obvious that that's the case. That as soon as you take a commutator of weight 4, it's that entity, meaning that commutator of weight 3 commute with anything else. If you have an element of this form, then you can commute with whatever other element in the group. In other words, in the parlance of group theory, these elements are in the center of the group. They commute with everything else. And then this is not trivial. It kind of follows from the equation that I showed before about xyx equal to y inverse x inverse y inverse. What's called the second angle condition of a group. And if you're curious, I can point you to reference where this is shown the whole simple elementary derivation on a couple of lines, but if you don't know which one it is, it's going to take, maybe like 10 minutes to figure out the right order. So we're going to summarize the important condition that we're going to use in the following. So like I said, the most important one to keep in mind is this fact that commutator of weight 4 are trivial, so that things of weight 3 commute with everything else. And it's spelled out here. So if you have a commutator of weight 3 and any W, they're going to commute. Another consequence, which also it's not obvious, but it's true, is that if you have two commutator of weight 2, those are going to give rise to a bunch of commutator of weight 4, which are all going to be trivial. And so commutator of weight 2 commute with themselves, which means that even though they are not in the center, commutator of weight 2 don't commute with everything else. However, on their own, they make an abelian group, because if you just have those elements, they're going to commute with themselves. So you have the center, which is going to be things that commute with everything. Those are the commutator of weight 3. And then the commutator of weight 2 are going to be things that commute with themselves, although they are not in the center. So they are in a subgroup. In fact, it's the largest abelian subgroup inside this group. Other useful identities, if you want to commute two elements in the wrong order, then it's just going to be the inverse, meaning that if you want to commute xj and xi, it's the inverse of xj. That's always true. In the case of Burnside group, because of the second angle condition, it also follows that you can pull this -1 inside. The inverse of the commutator of xj is the same as the inverse of the commutator of xi with j. So you got to get some sort of bilinearity. This is when it comes in and out. Unfortunately, that's all the binarity you're going to see. We're not going to be able to get, at least so far, we haven't been able to get any sort of advanced crypto functionality. I'll mention at the end that even public cryptography is a bit of a challenge in this setting. Okay, and then another important fact is that if one of the generator repeats, this is xi, xj, xi again, then it is trivial, which is going to, important. I don't think it's going to come out later, but in our notation, if you have something like xi, xj, xi, sorry, if you have xi, xj commutator with xi, this is going to commute. It's going to be equal to xi, xj commutator. Because this is due because of the fact that elements commute with their conjugates. And then some other useful property that you can kind of do rotations inside this commutator of weight 3. So if you have commutator of weight 2, you want to swap them, then you have an inverse coming up here. And this happens whenever you swap two elements. So if you do a cyclic rotation here, you're doing two swaps, so they are the same. So xi, xj, xk, the same as xj, xk, xi, and the same as xk, xi, xj. If you just swap two, you get an inverse. Those are going to be useful because later on, I'm going to like to sort these commutators. So those are going to allow me to say that you can always assume lexicographical order inside the commutator parentheses, because if not, you just swap them and there may be an inverse coming up because of that. All right, so now the useful thing in terms of talking about the group operation is going to be, okay, before talking about group operation, can I even test whether something is identity? We have some crazy equalities here going on. For example, before we saw x1, x4 inverse x1 equal to something else, which means that there is a long expression of this identity. How do I test for the identity? It's going to be an issue like we're not even going to be able to tell whether three elements are equal. So that's not going to be a problem because Burnside groups have a nice normal form, which means that for every sequence of, for every element, given as a sequence of generator and their inverses, we can quickly, in time, polynomial in the length of the expression or cubic in the number of generators, whichever is smallest, whichever is largest. So linear in the length of the expression plus cubic in the number of generators, you can turn that into so-called normal form. And so here I have the motivation why we care about the normal form. And the normal form is going to look like this. Every sequence of product of generators and their inverses in this group can be written as lexicographically sorted generators, maybe absent if the exponent is at 0, maybe inverted if the exponent is a -1, followed by lexicographically sorted commutator of weight 2, again 0, 1, -1 exponent, and then lexicographically sorted commutator of weight 3. Now, it's also not obvious, that's actually pretty easy to show if the things we can talk offline, that for every choice of exponent alpha, betas, and gammas, you get a different element, which means that the size of the group is exactly 3 power n plus n choose 2 plus n choose 3, which is essentially going to be cubic exponents, something in the order of 3 to n cubed, probably 6 or something. Okay, so the normal form and the uniqueness of the normal form is what's going to allow us to say that there is an easy test for equality. You just write them in normal form and you compare the exponents with. And the cubic that was mentioned before comes up because you're going to have a cubic amount of commutators of weight 3. And so even to write down the normal form is going to take cubic time in the commutator, in the number of generators. in this group. And you can, for cryptography, you can think of the number generators are some sort of security parameter for us. Maybe it's going to be half the security parameter, or related to security parameter. Okay, so now for one picture. Unfortunately, I'm not going to have a lot more pictures, so enjoy this one. It's going to be for the special case that there are two generators, and there's a special case for many reasons. One is that for this special case with two generators, you don't even get commutators of weight 3, because those are going to repeat the generators, and like I mentioned, those are going to be trivial, so they don't even arise. You only have 3 terms in the normal form, so there are going to be 27 elements in total, and it just so happened to be the same as the Heisenberg group. So if you know about Heisenberg group come up in quantum systems, just so happened that they're the same for a Heisenberg group for the case of n equal to 1, but they're not the same for two Heisenberg group for other values. So there's no other value for which you get the same as Heisenberg group. That's kind of interesting because Heisenberg group have a nice representation as matrix. And whenever I talk to people which are in cryptography, they tell me, okay, can you describe to me this group in terms of matrix multiplication? Embed it into GL2, GL3, whatever your choice, and show it to me so that you can do multiplication of matrices. And unfortunately, for the general case, there is no known polynomial size, polynomial order representation. Yes, you can embed this thing, but it's going to be exponentially big, so you're not going to be able to multiply them. Now, if you're curious afterwards, you can ask me about a variant to this problem where you mod out commutator of weight 3. If you mod out commutator of weight 3, turns out that then there is a small normal form. It's not really too small. It's like a small representation. It's going to be linear in the sides in the number of generators. So it's not constant, but it's still smallish. And we're looking into that as well. So if you want, you can talk about that offline. But for the case of two generators, a couple of things we can see, just to make sure you understand the basic concept. The quality, the cubic law that everything cubed is 1, you can see it in this triangle. So if you look at this item, this picture, by the way, is a so-called Cayley graph, which means we're representing the structure of the group by having nodes being the items in the group. And it's a colored graph in that the edges are colored with green or blue or purple, in this case, because there are two generators. In the case of the general Cayley graph with more generators, it has as many colors as there are generators. And they are directed edges. So the purple means multiplication by the second generator, and the green means multiplication by the first generator. And if you're following an edge in the opposite direction, you multiply by the inverse. So if you are here and you follow this edge, you multiply by x2. If you're here and you follow this edge, you multiply by x1 inverse, for example. And so you can see the cubic law, because if you follow the same direction 3 times, you go back here. And as well, you can look at things like where do the commutator live by following the corresponding edges. And yeah.
So this last line, what do you mean exactly by that? Is it a linear representation or?
No. So what I mean is that I don't know if there's a proof that there is no polynomial order representation, but we don't know of any representation of this group Burnside, the full Burnside.
What do you mean by
representation embedding into GL3. Maybe it's
GL3?
because these are all order 3. The exponent is always 3. I'm fixing exponent to be 3.
So the order is the size of the matrices?
The dimension, yeah, the dimension of the matrix, yes. Yeah, I don't know if that's standard. Sorry, I thought it was standard.
For n large enough, for n large enough, it's pretty infinite.
No, because I'm fixing exponent 3. Exponent is 3 here.
Oh, the exponent is fixed to be.
Yeah, the exponent is 3. This is always going to be finite. We know exactly the size. It's 3 power n plus n choose 2 plus n choose 3. So we know it's finite. We know many. Yeah, we know exactly the group structure. The size. The group structure not so much. However, we can't, easily put this in the matrix form. Essentially because of the commutator weight 3. Those are what mess things up. If you mod those out by looking at the quotient, turns out that you can represent them. And maybe that's interesting to look at them, but we're looking at the full picture for now, kind of like also try to see whether there's any advantage in looking into the modding out.
So
What?
So where are the how far back does this go? The knowledge of the structure.
The structure of the group already in the 50s, I think.
Okay.
I'm not sure if much before.
Sort of when Gilbert was starting out.
Yes, of course. Yeah, not Gilbert. Yeah. Yes, but I mean, he was not looking at this question. Really, he was looking more like the other. He liked this fact that for even exponent there was no proof until the 80s or something. Yeah. More questions? This is the last chance for picture. Okay. So now for the group operation, I was promising it's going to be a bit annoying, but we can handle it. It's going to be important that we have this normal form, which means that every element can always be thought of as a sequence of generators, which is going to be a sequence of length almost n generators, followed by a sequence of 2 commutators. I'm sorry, it doesn't show up. The green says 2 commutators. And then 3 commutators. So it's going to be the overall length of the sequence is cubic. Most of the stuff is going to be these 3 commutators. And now if you want to multiply 2 elements, what you do is you take them in normal form, then you stick them one after the other, and then you fix the fact that there are things out of order. How do you fix them? It's going to be in stages. It turns out it's going to be relying on these commutators, and it's going to require a lot of cubic time, which is optimal in this case because even to write down the answer in normal form is going to be cubic. So cubic here is nice. Okay, so the first step is going to be the easy one. We know that this thing, I mentioned that the commutator of weight 3, they are in the center, they commute with everything. So we can just move them all the way here. They commute with these guys and with these guys. They're going to commute with this. We can align them, add the exponents, mod 3, and we're done. And so in a cubic amount of time, we can get to this kind of shape. It's going to be cubic just because there are a cubic amount of commutator of weight 3. But each of them, it takes just constant time to deal with. Okay, so next we have something like this. We have to fix the commutator of weight 2. We have to move them all the way to the right. So in this case, we look at them one by one. We look at the last commutator of weight 2 here. And we have to make it travel to the right of this generator. Now, in general, they don't commute. So what's going to happen, you can swap them. You're going to have to introduce a commutator of weight 3, right? So if you have something like xn-1 with xn followed by x1, which is what's going to happen at this interface, modulo there's maybe exponent here, then you can write them as x1 followed by xn-1 xn, but then you have to keep the xn-1 xn x1 tricommutator, which then you can cyclically rotate. It's going to be the same as x1 xn-1 xn. So in other words, what happens is that to just move one guy by one position, you're going to generate a commutator of weight 3, and then to move it by another position, another commutator of weight 3, it's going to get all the way here, and you're going to generate the n commutator of weight 3. So in other words, to fix each single commutator of weight 2, you're going to incur order n cost, running time, because each of them is going to have to traverse order n generator of weight generators, and each time you're going to create a commutator of weight 3 to sum at the end. Because there are a quadratic number of commutator of weight 2, by linear time for each of them, again, that stage also takes cubic time. So you can go to a semi-normal form, again in cubic time, and now all you're left is a list of generators in lexicographical order, another list of generators in lexicographical order, and then the rest is fixed. So that's the second stage. Now the third stage is going to, of course, try to fix this. And again, the way you do it is you take xn and you make it travel again against x1. Now the problem, though, is that to do that, you're going to generate inside here, when xn travels before x1, it's going to create an x1 xn generator, and then an x2 xn generator, and then xn-1 xn generator. So just to fix one generator, you're going to create inside here new commutator of weight 2, and now you're going to have to fix those. Fixing each commutator of weight 2 was linear. Now we only have a linear amount of them, so it's going to be quadratic. So fixing one generator requires a quadratic amount of time, because one generator creates n commutator of weight 2. Each of them takes n time, so it means one generator takes n squared time to be fixed. And then you have n generator times n squared times, so it's again n cubed. So all three stages take n cubed time, but other than that, they're pretty simple. Like, in terms of implementation, a lot of this can be parallelized. Unfortunately, the last step is not easily parallelizable. We're working on implementation to try to get an handle on how fast this would be, but it seems like the cost involved would be pretty small. Okay, so the runtime for this operation would be cubic, which is as good as it gets because of the representation of the group. All right, so maybe I'm gonna walk through an example. Maybe I don't know if it's gonna be confusing. All right, so here we just have like an example in the case with 3 generator, x1 inverse, x3, x2, x3, and then x1, x2, x1, x2, x3. And even if I skip, I guess you guys are gonna have the slides, so you can look at them later. Anyway, so of course, the first thing would be to deal with the commutator of weight 3. In this case, there is no to fix. So the first stage is trivial because the first word didn't have any generator commutator of weight 3. So we already go to the stage 2, where we fix x2, x3 against x1. So we have to swap x2, x3 with x1. We do that here, x2, x1, we swap with x2, x3. And then that creates this commutator of weight 3. Okay, so then what we do, we fix it with just shifting the indices. We can always do that. And now we are going to have this commutator of weight 2 that needs to go right. That's easy because it's commuted with everything, so I can just swap them with x2. And now we can move over no, now here we just collecting. We notice that this is a square. Square means inverse, so that's what we get. At this point, we swap x2, x3 with x2. In this case, x2, x3, and x2 they just commute because things commute with their commutator. So x2 commutes with x2, x3 commutator. So there is nothing to no penalty to pay. Next, we swap x1 with x3 here because we are done with the second phase. Here we start the third stage. So we swap x1, x3, and that creates x3, x1 commutator, which is the same as the inverse. We also cancel this item out. Next, we swap these two. That's going to create a commutator of weight 3, which of course we can make the shifts. That's going to be possible to commute with the weight 2 because they are in the center. And at this point, we swap these two. They get a new commutator of weight 2. And finally, here we just swap the order. Here we just rearrange them because the commutator weight to commute on their own. And finally, these two simplify, and you're left with this. So if you forget about the steps, it's more like you can look at them offline. One interesting thing is that if you just look at the exponent of the generators, here you had x1 inverse x3 and x1 x2. The x1 inverse and x1 they did go away. So if you just look at that as a high order, like rough approximation, you can just look at the generators and sum them up. That's going to be easily tell you you're going to get something like x2, x3 here. But to get a handle on the commutators and the commutator weight 3, that requires carrying all the operations. So if you just care about the first order approximation, you can get it easily. We're going to come back to this. This is called the abelianization. When you drop all the commutators, you just look at the portion. Essentially, you force the group to be abelian. Then, of course, this is just addition of F3n. Okay, that's exactly what you're seeing here. We're going to come back to this point. All right, so the point was more like, so it's in the slide in the video to have the example. So to recap, the important thing to remember is there's a normal form. We know how many items we have. The group operation is efficient. By the way, we can also do inverses. It's going to also be a cubic time operation, although it's a bit simpler, it's a bit faster. But it's a similar idea to with the inverse. You just have to do the inverse of everything and swap the orders in reverse order. And also to remember that it's not commutative, but there are several important properties. The most important of which is that commutator weight 4 are trivial. So there are a bunch of things that are easy. A few other things that I'm not discussing. Conjugacy problem is easy in these groups. The word problem is easy in this group. This follows from the normal form. So going back to the original motivation, okay, so this group and B, they're nice, but how do we use them for cryptography? What's going to be hard about them? So the question is that we are going to be using them as an instantiation of something similar to the learning with errors. So here I'm kind of like switching a bit gears, going to something we saw yesterday about learning with errors. Here, I'm sorry for the acronyms. Here, LW is going to be for learning with errors. And let me remind you what the learning with errors setting is. That's this is an important interactivity assumption that has been used to come up with, among other things, fully homomorphic encryption. It's been pretty successful since that introduced it almost 10 years ago. Now it's 10 years ago, I guess. And what's the setting of learning with errors? One way to think of it is that you have a secret vector S in FNQ, in FQN, and you look at samples coming from the linear functions. So in other words, what you have vector space over a finite field, and there is a secret functional, there is a secret vector which defines a secret functionals, and you give out pre-images, vectors, together with their noisy image, with the noisy inner product of the samples with the secret, where the noise comes from a discrete Gaussian, small zero-centered, small deviation distribution, which for probable parameters which are on each side. And the assumption is that if you have samples of this form, where this distribution A parameterized by the psi for a random S, if you have sample of this form, they're going to look the same as sample coming from both sides being random. Of course, in this case, the first side is truly random, but the second side is an inner product, a noisy inner product. Instead, in the reference distribution, they are both random. And the LW assumption in its decisional form states that these are indistinguishable. There's no point at time are going to do that. Okay, so this is one way to think about the learning with error problem. And that was a decision version. There's also a search version where you want to find the functionals, although we are not going to concern ourselves as much about the search decision, the search version of our problem. So I'm only going to talk about the decision. Okay, so there is a lot that you can learn about learning with errors by looking at its geometry. And Daniele mentioned something about how they're really very related to lattice problems. However, there is also something you can learn by looking at learning with errors from an algebraic point of view, which is what we're doing here, like abstract algebra. So forget about the fact that these are vector spaces and they carry all this geometric information. You can think of this as an homomorphism between groups. So of course, this is much more than a group, but inside there is a group, an additive group. And also here, the vector space, the underlying vector field as an additive group inside. So you can just think of this as a homomorphism between two groups where you're giving away its preimages and noisy image of the homomorphism. Of course, inner function is more than homomorphism, but if you want to generalize this to a case where these structures are not necessarily vector spaces, you can just think of this as giving away preimages and noisy image of a random homomorphism perturbed by some noise in the destination group. So this is just a change of notation. What before was called a function, I'm calling an homomorphism within two groups. The two groups in the case of LW happen to be a finite field for the destination group and the vector space over it for the preimage group. And then there's a question of what do you make your noise? You know, like you must have some small noise which is well behaved in a sense. In the case of LW, that was the discrete Gaussian. That was what you wanted. And so if you want to generalize, you're going to have a parameter which is going to be distribution psi, and you're going to have to figure out what distribution you should be using. It's going to be some noise in the destination group. Of course, you want to be small in some sense, but you know, what does it mean? So here is just a recap of the notation. We're going to have, if we want to generalize it in an abstract way, you have just two groups, G and P. They need to be compatible in that you must be able to have homomorphisms from the first to the next. You know, somehow they need to have the same structure, otherwise you can't have homomorphism into random groups. For example, you can't have a homomorphism between ZP and ZQ for coprime P and Q unless it's a trivial homomorphism and everything to the identity, because ZP has some law, everything must to the power P minus 1 must be 1, and ZQ has some other law, and they don't match up. So these must be compatible. You want them to have lots of homomorphism with the two of them. The secret is going to be one such homomorphism. Now, in principle, you can choose your group to be infinite, although in what follows, I'm going to use instead finite group for the choice of GMP, and you can guess that I'm going to be using Burnside groups. That's why I introduced a Burnside group before. But you can do this, you know, at least abstractly with the infinite groups. And the question is, what do you choose for your distribution where you take the preimages and for distribution for the errors? Because in infinite groups, it's kind of tricky to come up with right distribution, and we're not going to look into that. And then, of course, you get a parametric assumption which depends on the choice. It's going to be just distinction samples of this type, which is preimages noisy image, from just random sample. And again, here, if you have an infinite group, you don't want uniform. You want some other sort of reference distribution. But I'm going to assume we have finite groups here. And you can make this assumption when the secret is random. Now, the rest of the talk, I'm not sure how much more time I have, is going to be about the fact that actually, for some choice of the group, it doesn't matter whether you choose your secret to be random or you took it arbitrary. So this is going to have some strong random self-reusability property whereby if you use a random secret or if you use an arbitrary secret under some condition, it must be surjective, which is going to be overwhelming in the case if you take it random. It's going to be the same hardness. Okay, so it's not going to matter where you take your secrets. So again, just to hammer this idea down, these are the same picture just to show how LW really is an instance of this framework, where you choose your group G to be just the additive group inside the vector space, FPN, and you choose your group P to be the additive group inside the underlying field. You choose the discrete Gaussian as your distribution for the noise. The homomorphism has the linear functionals, and you select secret keys by just taking a random homomorphism, which is a random vector. And so when you take an image, you know, just take a random value here, and it's going to be given E plus E. This is inner product. And of course, there's going to be a switching notation, because for vector space, usually the additive notation. Instead, here I'm using the multivariate notation, because we only have one operation. Okay. So, and of course, here this is parameterized by distribution. So generalizations are nice, but they don't make too much sense if there's only one instance. If you generalize and there's only one known instance of the problem, then you may as well just study the problem. So that was our initial motivation for coming up with an alternative, and that's where we're looking for lots of homomorphism. And that's where we came up with these Burnside groups. Turns out that the key property that the Gilbert bounds like so, in the reason why we want the Burnside groups, is that they are relativity free, and I'm going to come back to what that means in a second. But briefly means that you're going to have lots of homomorphism between two groups with different number of generators. you can have lots of morphisms. They're going to be your secret key. So you want to have lots of them to choose from. So if you instantiate this setting with Burnside groups, what you get that your preimages are going to come from a Burnside with many generators. Exponent is always going to be 3. But your preimages are going to come from a Burnside group with many generators. And we don't really have like good experiment to show what the number should be, but we are thinking something like 100 should already suffice. Compare this with 1,000, that's what you need for LWE. But again, we don't know too much. I'm gonna come back maybe like later into that. So you have this big group here. So if you have 100 generators, it's gonna be, the size is gonna be roughly 100 to the, so 3 to the 100 cube. So it's gonna be a pretty big group. And then you're going to take as a secret a random homomorphism between Bn and Br, where R instead is going to be a constant. So the target group is going to be a small constant. You can think of this as something like you go from LWE when you choose your exponent, your module to be 3. So if your module is 3, then you're doing from F3n to F3. And of course, you have to change it because you can no longer talk about Gaussian if you have only 3 items. It's more like a Bernoulli. So it's going to look more like an LPN, learning party with noise, than LWE, but it's the same kind of feeling. Okay, so that's your target, your source group, your target group. These are your secret keys, and then samples are going to be random for images, followed by application of your homomorphisms to them, and then you're going to select the noise from some distribution. That's what's going to take some work to figure out what distribution to use from. Now, in the case of LWE, it helped that there was geometry, and so we talk about this discrete Gaussian. It has a nice spherical symmetries. Here we don't have a lot of geometry. Fortunately, you can recover some geometry for any group with the Cayley graph. We saw the Cayley graph for the case of 2 generators. It was the ball with the 2 color edges. And in general, the Cayley graph has an associated concept of Cayley norm, which means if you have an item, and you place it in the Cayley graph, what's the shortest way to get it from the identity? You're going to write this item. There's going to be a canonical way in Burnside. Everything can be written in something of length 10 cube. But maybe if you write them out of order, there's a shorter way to write them. And we call them the Cayley norm for the item. Now, it turns out that in general, computing Cayley norm is a hard problem. It's an NPR problem. For Burnside groups, we don't know. We weren't able to find any kind of references. So first plea for help, if you can point us geodesics in Burnside group, and if they are not known, if you could come up with such a result, it would be great. And specifically in the case of B3N, it shouldn't be too difficult, but we are kind of like short on tools to figure that out. And so far, what we've been doing is working with a constant R, so that you can just brute force this guy, because you're just going to build a table of all the items and look the first time you obtain them, and so you can brute force it and get a small table of like 3 to the 14 entries, whatever it is. And so that's what they're doing now for geodesics. But it'd be nice to be able to compute them fast. It looks like there should be some recursive algorithm for that. So it seems like it's a low-hanging fruit, but it probably requires some deeper understanding of the algebra than we have right now. So anyway, we're working with the case of small r constant, so we can ignore this point about the efficiency of computing Cayley norms. And then what we do for perturbing an item, essentially what we do a random walk starting from this item and appending to that. An item is just a sequence of generators. We just append to that another sequence of random generators, where we choose exactly a permutation of all the generators, and then we take random exponent. So in other words, you can think of the noise as a random point in the ball around identity. Even though this doesn't have a lot of geometry, you can still think about ball by talking about this Cayley norm. Although it's not exactly like that, because you don't allow the same generator to repeat twice. You want essentially every generator to occur once in random order. So you select a permutation of the generators, you pick a random instead exponent, and that's your element. That's your noise. Just a product of a random ordered sequence of generators, which may be present, may not be present, but each of them is only present once, if it is. And then your images are going to be disturbed with this noise. Okay, so that's the distribution. It's gonna come back to why we choose distribution in a moment. I'm gonna also denote distribution with B. Unfortunately, it's the same B as this. It's a script B. The reason for that is because it's like a ball, so it's kind of usable to think of that as a ball over the Cayley norm, but it kind of conflicts with the notation. So I realize maybe it's not the best choice for of notation. Yes, Chris. It doesn't matter, although you're gonna have to be consistent. No, it doesn't matter. I just chose to do it, because usually LW do SA plus C, so but it doesn't matter. And now the assumption, of course, it's gonna be that it's gonna be parameterized by the distribution of noise we choose for some secret homomorphism. When the assumption says that if you take a random homomorphism, then pairs like these are distinguished from uniform pairs, where both items are random in their domain. And they're both finite, so you can just talk about unit distribution. And then what I'm going to tell you next is that actually this assumption has a random self-reducibility trait. So it doesn't matter whether you take your secret at random or whether you just choose any secret which is surjective from Bn to Br. And now surjective here, it's going to all, and epi here means epimorphism, so they are surjecting homomorphism. And it's almost going to be for sure they are surjective because you're going from a big group to a very small group. So it's going to be overwhelmingly likely that you're going to hit the entire group. So even if you take a random one, it's going to be surjective with overwhelming probability. Okay, so next I'm going to talk about this result, this fact that the assumption is defined to be for random homomorphism, but it is the same as for arbitrary homomorphism, meaning that this problem has a strong random self-reducibility. So why do we care about random self-reducibility? If you remember my pitch from the beginning, I wanted to convince you that we're looking at a problem that they have a hope of being intractable, that they're going to withstand cryptanalysis whenever you guys decide to try to attack them. And why we think they're going to be secure? Because they have this circumstantial evidence in the form of random self-reducibility. So Daniele talked about random self-reducibility yesterday. And briefly, the point is that, first of all, it's something that's shared by most of the problems that have withstood the test of time. And in particular, it comes with different type of strengthness. Problems like LWE are more strongly random self-reducible than problems like discrete log. You can't randomize the modulo in discrete log, but you can, essentially, in the case of large problem, like Daniele was talking about, there's essentially only one instance, and you can fit smaller dimension, bigger dimension. And something like this is true for the Burnside group. There is an image, an homomorphic image of B10 inside B20, and there's one of them inside B100. So you can think of them as just one instance for a bounded like N, and they all kind of like fit inside. They're smaller instance of the same problem. So they're the same kind of flavor of the strong random self-reducibility that problem like lattice problem have. And it's also important for cryptographic application because it means there are no weak instances. If you're going to build a cryptographic system out of it, your secret keys are going to be homomorphic. And if you take a random homomorphism, it's going to be as strongly secret as any secret. So it's going to be easy to use. And vice versa, it's going to be easy to break. If you want to break this thing, if you just break it from a random instance, you know that you can break it all the time. So it's not going to be like you're going to get into hard instances and easy instances. And it's going to be, so one way to say is it's easily falsifiable. So there's going to be an easy way to break it if the assumption is false. So that's why we think that random self-reducible is a useful property to have, and that's why we went after this kind of like approach to define problems. And okay, so how do we establish this property of random self-reducibility? Well, we want to understand that if you use a random key or an arbitrary keys make not much difference. Now keys are homomorphism, so you better understand homomorphisms if you want to understand how keys, whether it matters that the key is random or not. And so the first thing we need to do is understand a bit what how homomorphisms from Bn to Br work. And the crucial part here is going to be this property of freeness. Like I mentioned before, this Burnside group, I literally call them free Burnside group. And essentially, by definition, these are groups such that the only property they have is exponent 3 condition, and they have no other restriction. And really, the definition is that these are those groups such that for every other group that has exponent 3, it's always possible to see those other groups, P of exponent 3, we can always see them as homomorphic images of the free Burnside groups. So turning this on its head, this means that if you have a Burnside group with a generator, and you have any group of order P, for example, F3 N, that has order 3, then you can always extend the mapping of the generators of Bn onto the group F3N, onto the group P. You can always extend that into an homomorphism, and that's unique. There's a unique way of doing that. In other words, you can count the homomorphisms from Bn into P, or in our case, we're going to be concerned in the case that the second group is also a Burnside group with fewer generators, so it's also has condition exponent 3. So you can count the number of homomorphisms from Bn into Br, because all you have to do is take all the n generators of Bn and map them into an arbitrary, whatever element you want in Br. And there are this many elements in Br. There are 3 power r plus r choose 2 plus r choose 3 element in Br. And each generator of Bn, you can map it to wherever you want. For each of them, you get a different homomorphism. So to get an homomorphism is also because we're going to be wanting to select a random key, which means a random homomorphism. How do you do that? You just select n random images in Br. You say, and that is going to be 4. So they're going to be element in B4 are things of the length 3 plus 4 plus 4 choose 2, 4 choose 3, so 3 to the power 14. And so your secret key is going to be, if n is 100, it's going to be 100 elements, where each element does 14 tricks, like 3 over 14 is the elements. So you have this many homomorphisms, which means that it's exponential in the number of generators in the first group. That's what they think our security parameter, and that's good because you need to have an exponential size, an exponential space for keys. So this is the first thing we want to understand about the homomorphism. Now, in order to understand the homomorphism between non-abelian groups, what we're going to be doing is going to turn into the abelianization. And for people that haven't seen this kind of group theory before, abelianization is a process by which you try to turn non-commutative things into commutative, more familiar commutative linear algebra. And in our case, it comes into three shapes. We're going to abelianize groups, we're going to abelianize elements, and we're going to abelianize maps, homomorphisms. So let me start from the first one. The abelianization of a group is just going to be taking the quotient by its commutator subgroup. So quickly, what you can think of is, killing all the commutators. I was talking before for the case of Burnside, you have the element, you have the generators, then you have commutator weight 2, and you have commutator weight 3. The abelianization is just going to kill the commutator weight 2 and weight 3. One way to say that formally is so that you look at the subgroup generated by the commutators, which is Bn here, so just the product of commutator of weight 2. They don't necessarily have to be basic commutators. The D and W can be any elements here, not just generators. And then you mod it out. So because they're arbitrary, so this captures both weight 2 and weight 3 commutators. When you mod it out, you get the quotient is going to be an abelian group, which is F3n. So that's the abelianization of a group. In general, in our case, the abelianization of Burnside of n exponent is going to be the vector space F3n, although we only look at the additive group inside that, F3n. So that's the first thing. Next, the abelianization map, which is how you map from the full group into its abelianization. That's what I discussed before in the example. If you have any element in the full group, in the Burnside group, that's just a list of exponent lists. It's an exponent list for generators, commutator weight 2 and commutator weight 3. Then the abelianization is just going to keep the prefix, which are the generator list, in the order alpha 1, alpha 2, alpha n. So of course, you can see that this is a map, and it's also an homomorphism, although it takes a little bit of calculation, but it's essentially the example that I showed before kind of shows that. There's going to be the abelianization map. I'm going to denote with rho n, the map that maps Bn into F3n, and also with rho r, the maps that go from Br into F3r. Okay, so of course, for every number generator, you have a different, they all do the same thing, slightly different than the signature. Now, what does it mean to abelianize a homomorphism between two Burnside groups? Well, what it's going to mean is to make sure that this diagram commutes. So let's look at this diagram, again, for category people and topology people, this is like, bread and butter, but just to make sure it makes sense for everybody. So you have two Burnside group, the preimages and the images group. N is like 100 and R is like 4. And your secret key is a homomorph between the two of them. Now, to abelianize it, it means to look at the following. You start from Bn and you abelianize it into F3n. Then you look at Br, you abelianize it into F3r. And now, you look at the composition of phi with the rho. That's going to be a map from Burnside group into an abelian group. Now, by the universal property of abelianization, this map from Burnside to abelian splits as first abelianization and then an abelian map between the two abelianizations. So again, it's like follow from a general theorem. In our case, what it means is that whenever you have a phi from Bn into Br, they'd always define a phi bar from the abelianization of Bn and Br. Now, the fact that it's unique, I think it's specific to Burnside. It is unique in our case. I'm not sure it's always unique. So, but in our case, it's going to be unique. And so it's going to be that map defined so that this diagram commutes. So if you follow a diagram from an element down to here, if you first map it homomorphic, then abelianize it, it's going to be the same as first abelianizing and then map it. And these maps are just linear algebra, okay, map between vector spaces. So in order to understand the property of these secret keys, we're going to be using this concept. And in particular, before we do that, Alex, how much time I have? Okay, so maybe I'm going to take like another 10 minutes. Okay, so before I keep going with that idea and see how it helps us showing the randomness of feasibility, I want to use that tool to show another thought. And in particular, often one concern that people raise when they look at this the first time is, okay, you are trying to go beyond LWE and come up with a different assumption that hopefully is independent. And maybe even if there are attacks on LWE for specific settings, maybe this setting is secure for smaller parameters. So it may look like you could actually try to use abelianization to reduce this problem into LW and say, well, if that were the case, that would be a problem. because that's not the case. But just what I'm trying to show, that's not the case, is the following concern. Do we need LWE to be strong, to be secure, for this to be secure? Is there a reduction so that the only way for this to be hard is for LWE to be hard for small LWE for over F3? So it's not really LWE, it's more like LPN, but the same kind of structure of an abelian group. Well, if that were the case, it kind of like killed the motivation of going after non-abelian groups. And at least stabilization does not suffice. So what I'm going to show here is that we don't have any way to show that they're independent, but the obvious way that is you start from the samples of the BN LHN problem, which are sampled in the non-commutator case, and you Bionize everything, throwing away the commutators. That's going to make your task impossible, literally impossible, like there is no way to distinguish it. So if you want to break this problem, you shouldn't look at LWE, you should try to look at the commutator parts. So let's see why is that. Now, the assumption we are making is that sample of the form A if you have AE, where A comes from the big Burnside group, and if A is the small Burnside group, where the noise is this random walk of small length, we assume they are the same, indistinguishable from pairs that are both random. So, of course, this approach that I'm talking about optimization, this rho should be rho n and rho r, because there are two components, that's why I'm just calling it rho. One approach to try to solve this would be, let me just throw away all the commutator information from A. That's going to be just rho of A, keeping the prefix list, just the exponents. And let me throw away all the information about the commutator in rho A in phi A of plus times E. It's going to become an element in F3n. So abelianization of the map, phi bar of A, plus abelianization of the rho V. Okay, so yeah, this should be phi bar of rho of A, not phi bar of A, phi bar of rho of A. So, and then, of course, I'm going to try to see whether the distribution you get in this case is easy to distinguish from this, or whether this task to distinguish from this is the same as LWE. And instead, what you notice is that, of course, because this was random in its domain, and this is an homomorphism, and it's a surjective homomorphism, then it's going to be random in its codomain. So rho of A is random, and so it's the same as structure as here. How about this portion here? Well, I don't know about this part, because I'm applying homomorphism, you know what happens. But rho of E, the optimization of the noise, remember what E was. E is a randomly ordered product of the generators, where each exponent is just random. So if you throw away the commutators, you just are left with a list of exponents of the generators. And I'm telling you that the list of exponents was chosen randomly. So rho of E, by definition of distribution, is going to be random. This quantity here is a random vector of R dimension. So it's going to be like the one-time path. This item is random. It's exactly random. And so what you get here is that the target distribution, if you Bionize, it becomes the same as distribution. So there is no way to tell them they are the same distribution. So you can't easily use LWE to break this assumption. It may be possible some other ways, but it looks like if you throw away the information from the commutators, what you're left with is exactly the same, whether it comes from the random distribution or from your distribution, from your distribution. So that suggests that actually these problems are independent. It doesn't prove that they are independent, but it suggests that at least stabilization doesn't immediately work, and it's an easy, to start understanding what the stabilization does. And sorry about the typo I had before. All right, so hopefully this is independent from LWE, and now for the fact that this is random self-reducible, the proof is going to compose of two parts. The first part is going to be that if you have, it's going to say what we call a domain reshuffling trick. That's a generic trick that's also true for LWE, for example. And by the way, also ring LWE and modular LWE, all the generalization LWE of which I'm aware of, they also fit into this LHM framework. Of course, we can't really understand. We don't learn a lot much more about this problem by looking at that, except for this trick, which is not used in the case of LWE because you have so many other properties that you don't need it. But I'm going to mention a randomization trick, which is also true for LWE. It's just going to say that if you have a pre-image, if you have a sample from LWE, you can get a sample under a different secret by not messing with the error part, just messing with the pre-image. And then, usually this is going to be a weak trick. It's not going to be fully randomizing your problem, except that for the case of Burnside group, and by the way also for LWE, it fully randomizes the problem. So it gives you a full random self-reducibility among the class of surjective homomorphisms, which, as I mentioned, they are an overwhelming fraction of all the homomorphisms, because BR is small and BN is big. So these are going to be the two steps. The first step showing the domain reshuffle trick, and the second step showing that this trick is actually complete for the case of Burnside group. So domain reshuffling is essentially just a simple algebraic manipulation. Just to set notation, what I'm saying, suppose in general you have the two groups Gn and Pn. You have a pre-image sample where B is a noisy, in this case you know it's a sample from distribution, so B is a noisy image of A under the secret homomorphism from some small noise. then if you take some automorphism, actually it suffices for it to be any permutation, but in general we're going to be looking at homomorphism, so we want it to be an automorphism. If you take any automorphism alpha over Gn, and you pre-process all the samples by applying alpha inverse to your homomorphism, to your pre-image, then the sample you get, A prime B, by not touching B, is going to be a sample for the problem with the different sigma key, with phi composed with alpha. And unfortunately, you have to apply alpha inverse if you want to have alpha here, and so that's why I have the alpha inverse notation there. Okay, so what this is saying is that you can randomize the domain of the sigma key. You can go from one sigma key, samples under this, to another sigma key, sample. So you can take a sample under phi into a sample under phi composed with alpha by pre-processing all the first items of the pre-images by alpha inverse. And this is just an algebraic manipulation. It's always true. And you just say, well, if you look at alpha inverse B, that's a sample. I want to show that alpha inverse B defined like this is a sample under this. By definition, alpha inverse B, so B is phi A of times phi. We can write A as phi as alpha inverse. We can look at this as alpha inverse alpha as alpha prime. And so this looks like alpha prime, and then the image times the error. And because alpha is a bijection, then this also is randomly distributed in the group. We didn't touch the noise, so it does a proper distribution, and so this is a sample from what you want. And this is also true from LW, but in LW you don't need this. You have abelianity, so you can work on the, you can also touch the error, which we can't easily. So this is a simple observation that says that you can already do some randomization by just applying an automorphism to the pre-images, just to the pre-image component. And then what happens is that in the case of Burnside group, and also for LW, of course, this is complete. You can take any epimorphism, any surjective homomorphism can be moved into another surjective homomorphism by the same number of automorphisms. So, you know, I'm going to only show that they exist, but it turns out that they're the same number. And so if you randomize it like that, there's going to be this, if you take a random automorphism, it's going to be the same chance of moving your sigma key phi into any random sigma key phi star. So long as your initial one was surjective, the destination is also going to be surjective. And that's going to mean that you can always randomize. If you have an arbitrary, you can always randomize it. And that establishes our reduction. And in fact, that's going to be true also for the case of search. This random sensitivity is also true for the search problem. Although we don't know how to use the search problem for other reasons. So that's why I'm sticking with the decision. Okay, so the key here is this transitivity argument, that every homomorphism phi can be moved into another target homomorphism phi, if they're surjective, by some automorphism alpha. And I'm going to try to quickly show why that will be true. So first of all, what they're talking about is the following picture. So I have an homomorphism from Bn into Br, that's phi star, that's my target homomorphism, the one I'd like to get. And I have an homomorphism from Bn to Br, that's phi. And I want to show that I can always obtain phi star by first doing applying an automorphism from Bn into Bn, and then doing some random homomorphism phi. So in other words, what I need to do is to build a beta here given phi and phi star. So I have this part and I have this part, and to come up with a beta, which is a bijection. Now, similar arguments, like I said before, just of the diagram chase, show that it's always going to be possible to come up with some homomorphism, not necessarily bijective, from Bn into Bn, that's going to satisfy this property. Because essentially what you can do, because they're all surjective, you can look at the images of the generators under phi and define beta so that it maps the generators into those items. Because this is surjection, so you can always find elements that hit any value here. But the trick is that what you get like that is not necessarily going to be an automorphism. What you could get is maybe an homomorphism. In other words, the problem is that you're going from a big space down to a small space, and here also from a big space down to a small space. It may be that this is going to give you a way to go from here to here losing something, and then from here to here losing the rest. So it is possible what you are getting, it's not an automorphism. And if that's where they all you get, then the randomization is not complete, because it could be that there are, if you just take a random homomorphism, they're mapped more into some phi than others. So you don't have the uniform distribution. So what you want is to show that you can always patch this beta so that it's always going to be an automorphism. And again, the way you're going to be doing that to show that the function that you get is always going to be homomorphic is to do the same. We're going to do that over the Beyanization. So this step is going to work over the Beyanization, and it's going to depend on the following fact, which is non-trivial, and it's like the main technical part in the proof, that a mapping from Bn into Br is going to be bijective. It's going to be surjective, if and only if the corresponding map from the Beyanization is surjective. And then when you do the case that Bn and Bn are the same, that's going to be our case for the automorphism. So really what we need is this diagram when these are all n, but the theorem is true also for any two dimension. And so what this is saying is that there is a lot that you can learn about the homomorph of these two Burnside groups by looking at data Beyanization. They don't suffice, because if you want to just do a Beyanization, the assumption kind of becomes impossible to break, but they tell you a lot. So, and in particular, this property that, like I said, this is surjective if and only if this one is surjective. One direction is kind of obvious. It's again the universal theorem. If this is surjective, this must be surjective. The other direction is what's a bit more interesting. It relies on the fact that it said that if this is surjective, then this must be surjective, because this being surjective means that the images here generate the whole image. But because this is a Beyanization of something else, there is a way. This depends on the fact that this group is nilpotent. Nilpotent has to do with this property that I was talking about, commutator of weight 4 being 1. And so turns out that if you have a generating set of this of the Beyanization, you can lift it into generating set for the before you Bayanize it for the original set. And this is actually what you do. If this is and it's more than just if there is a R surjective, then there's R surjective. If you know a base for the domain, you're gonna know a base for this domain as well. So they are effective. You can actually also do them. So that's all I want to say about this. This is the technical lemma that implies what I was saying. For the nilpotent groups, if you have a generating set for the Beyanization, then you can lift that into a generating set for the original group. And now, just like just one slide on the application. So like I said, our motivation was more, let's come up with a problem that is arguably going to be intractable. And then of course the challenge is going to be, let's use it for cryptography. So unfortunately, giving up a binarity costs us a lot. We are not able yet to find a way to use this for public key encryption, but you definitely get pseudorandom generators, 1-bit encryption, symmetric encryption. We're working on PRFs, although we don't have that yet. And the idea for bit encryption is you can do LWE at least in the symmetric form. So what's the idea there? Well, the idea is that you're going to encrypt 0 with the noiseless images. So, sorry, you're going to be encrypting 0 with the samples from distribution, so random A, and B, which has a small noise. So we're going to be encrypting 1 with random A and B, which is far from an image of Phi of A. How do you ensure that B is far from the image of B of A? When the bit is going to encrypt is a 1, you tack on an item from the destination group which has a big Cayley norm. And because we can tell Cayley norm in this group by brute force, then somebody who has a secret key can run this test. Can take the second portion, calling it B prime, can multiply by phi A inverse on the right, on the left. That's going to cancel out the phi A. So you're going to be left with the E times tau if tau is present, or just E if tau is absent. Now, tau here is an item of big Cayley norm, and because instead the error is a small Cayley norm, and because adding them together is not going to change the Cayley norm of tau much, if this item is big, this means the tau was there, which means the encryption was a 1. If the item is small, this means the tau wasn't there, which means the item is a 0. So, and it turns out that you can improve the efficiency of this by having one point here and many homomorphies. You can have your key bigger, and then you apply all of them with the same pre-image. Similar tricks you can do with LWE. And the challenge is to extend this to be public key. And of course, there'll be, that's what they're working on. And the problem there is that the usual trick of publishing encryption of zeros and having the encryptor choosing a random subset of them and multiply them together works in the case of abelianity because the error nicely go together and small error stays small error. Here we can control the error if you multiply small error together, it stays small. But in our case, you'll be getting a mix of images and error, images, error, images, error. And we don't know how to tame those. Those may be growing wildly even though the error is small. So that's kind of the challenge. And we're working on that, but we don't have that yet. So other mini crypto application, like things like PRF, it seems a bit more promising. I'm sorry? Yes. So smallness is going to be Cayley norm. So what I'm saying is that we're going to be brute forcing that because our destination group is small. Yeah, the destination group is going to be B4. Yes, but then LW probably would have been necessary condition for this to be hard. Yeah, that's true. That's true. We couldn't come up to other. I mean, yeah, that's true. That was the one we were able to come up with, like where the noise, this property that if you realize it is uniform. We couldn't find another like one that has an easier test for small. Yeah. So we wanted that because we want to, we want to rule out like dependency on LW, and we can't really rule it out, but at least I want to defend from abelianization. So that was like the reason for having distribution there or the way it is. So that otherwise, if you require LW with Q equal 3, why are you going on abelian, right? Yeah, I mean, that may be true. We wouldn't find other sets. So the reason for that was to avoid that exact attack. I mean, at the beginning, we were thinking of like using things from the center, right? You can use for the noise, use the center, right? Then with the items in the center, they commute, you get public key right away. But the center, then you need LW to be hard. Like the case P equal 3, that optimization actually requires you. If things are in the center, it goes away. I think that, yeah, actually it's trivial. It's actually even worse than that, you're right. Then it becomes a linear system. Yeah, there is no noise, then it's trivial. So actually it's broken, it doesn't even require, it's noisy less LW, right? Which is a Gaussian elimination. Thank you, Dog. Right. So that's that. I mean, that's the summary. And, like I was saying, our point was more like to go for intractability. So a lot of the properties, so we use them for that. And as evidence, we show this random surfaceability, and we're working on application. And all sorts of things that we could use help on are like, solving this algorithmic equation about Burnside groups. Like, geodesics on Burnside group would be great. Also, figuring out whether the problem is hard, even with no noise. Like in the case of Gaussian elimination, that means LW with no noise, it's easy. But if you use a noiseless version here, if you just have a bunch of free images and images of homomorphisms in Burnside, is it easy to solve? Can you solve the system? Can you figure out the homomorphisms? How many samples do you need? Like, I don't think it follows just from the fact that you can organize the maps. So, I mean, it could be.
You can do Gaussian elimination on if you organize the functions. If you use the same order of the columns,
Yeah.
Then what you do for the multiplication will help. You can eliminate the first column first.
I think what you get is you learn the abelianization of your homomorphisms, but there are many BN homomorphisms that have the same abelianization. So I think what you get. I'm sorry, learning the abelianization. Yeah. Yeah. So what I'm saying is that we use the randomized version of the problem, with the noise, because we believe it's going to be stronger. But even attacking the noiseless version, for which I'm not sure that even the other property discussing hold, I think would be interesting. And you seem to believe that it clearly works. I'd like to see numbers. Like, okay, so if it's errorless, then with these number generators, it takes this much time. And then the question would be, I think for the decision version, yeah, I think the decision version, if there's no noise, it's broken. But the search version without noise, I believe, is not broken already. It may not be easy to break.
So you're saying that either I'm seeing, so I'm seeing pairs of A and then P of A times either the identity of tau?
No. So I'm saying you're just seeing pairs of A and P of A,
Okay.
and you want to figure out phi. And you can figure out the abelianization of phi by using abelianization, but you want to figure out the entire phi.
Yeah,
That's easy to recover everything, not just abelianization.
I mean, so what you do is, so you learn the abelianization, and that tells you what the abelianization of P of each of the generators are. And then what I want to do is, instead of learning the abelianization of that, I want to learn P of the generators modulo the triple conjunctors.
Okay.
And so the point is that, well, I know what they are mod single conjunctors, double conjunctors, or however you call them. And so then I know that they're equal to the following times, whatever commutator's powers they are. However, the result now of any P of A is a linear, is known up to those powers that I have. on the other hand, like if I modify by powers, everything should be a billion in the way that I modify this.
But you're gonna learn theory. I mean, yeah, there are very few generators, right? But
And in fact,
I'm not sure you can
any
test for
set of
that,
things
right?
generates the abelianization should generate.
Can be lifted to generator. Even it's like, yeah, you may be right actually. Yeah, so okay. Okay, so maybe there is a way. I thought that you could only learn easily the abelianization, but maybe from that you can lift it to the full, you're not going to be able to get a lot of homomorphisms out of it because it's got a lot of structures. Yeah, but it's going to be an exponentially many. You need the SR to be. Yeah, these homomorphisms maybe are going to be present then, but I don't think it's going to be easy to generate them because it's good not free. So you can't just say I'm going to pick. You can't just generate an homomorphism by saying here are the generators of Sn. I'm going to map them somewhere. I'm going to get an homomorphism. It doesn't work like that. But that's a pretty big point, right? Because you need to be generating random keys. For which you can easy. Yeah, and doesn't the next one has to be small, but like, then you need to be able to operate on it. That's why we want it small. Actually, the reason why the second one is small because we need to do the norm on it. Compute norms on it. Yeah, so if you have another setting where you can do the geodesics destination, you don't need the destination to be small. Actually, it's gonna make your key space bigger. So what you need is we're looking at other, we couldn't make it work for the symmetric. We thought about that. We looked into Rick products of P groups, and we couldn't make easy generation or random homomorphisms without essentially getting. The next component would be to get an error distribution where you don't need LW to be hard in the corresponding setting. So these were the two ingredients: going away from LWE and getting lots of homomorphisms and being able to generate them randomly easily. So freeness helped in one side, and the distribution helped on the other, and that's how we got this one. I mean, I'd be happy to see other instantiation, like that'd be great.
I think that this sort of thing is run into
True, but I mean, F3N is solvable, right? It's a billion, and LW is secure.
Well,
I mean,
fine. I mean, but I feel like it's going to be. I feel like this is going.
Sorry,
to be,
so?
Yeah, and I feel like this is going to be no harder than LW.
I mean, the reason why we hope it's easy gonna be is because the representation are big. LW representation are dimension 1, and so right there should be some additional
Well,
hard.
I'm saying you can probably get into it up here. You can attack it by sort of abelianizing it in various stages.
And that's what I don't buy. I mean, that's why I was, I understand that this only, what I showed was only showing one aspect of it, but I think that that's exactly what the error is trying to avoid. I mean, we may be wrong, but like our belief is that the distribution of error kind of like randomizes enough that if you just do abelianization, it's not going to work out. I may be wrong. I mean, I'd be happy if you can guys are like, point me to more concrete. Even attacking these like, for 100 generators or like 50 generators, it should be easy. With error, right? With the distribution of error.
I'm not sure that that's going to be. I think that might be approximately as hard as learning with errors on, if you choose 3 dimensions.
There will already be, like a savings, right? If you can, one of the issues with the is sizes. If you can save, yeah, we don't, yeah. I mean, I don't know. Maybe the comparison. It could be the same technique to break one. I'm gonna break the other. Like a technique for RSA works for discrete log for some reason. right? And they have different problems. It could be, but like, at least want to make sure that they are not the same problem. Otherwise, it's pointless. Could be pointless. You're saying it could be pointless no matter what, and I can't prove it otherwise. We don't know of anything other than urbanizing and then brute forcing. Like essentially applying LWE attacks, which are exponential, and then brute forcing the other components. Maybe actually faster to the second step because people seem to believe that you can recover the rest once you know the organization. But even that, like, no, it's more like LPM BKW kind of attacks because the model is 3. So ideas like the BKW. I think there is something that can be done. I forget. Maybe, yeah, we don't have a lot of democratic analysis. I think one of my co-authors was looking into it, but I'm actually not sure myself. That's true. That's true. So maybe there is no. I don't know what's the best attack for this. We haven't looked a lot into like catalyzing this.
The question is whether it's going to be order in cube or
yes. N cube over 2. Yeah. That's as far as, but we haven't looked at it a lot. Yeah, it's more than expansion in cube, right? But you're right. Expansion is expansion in N.
Unless you can get all to the
yeah. That's true. That's true. So maybe it's gonna be like then 2 to the R. Yeah.